This lecture is called Protection from Mayhem, and it's going to introduce us to the idea of the law of conservation of momentum, or LOCM. It says, sometimes thinking too much can destroy your momentum, and it's by Tom Watson. So, we want to look at our learning goals, and the first one is that you should understand momentum as a conserved quantity. There are very, very few things that are conserved, but they are energy, mass, okay, which we've already talked about, momentum, which is a new one, and then angular momentum. There are very, very other few things that are conserved, so we can use these ideas of conservation very efficiently when we're looking at a lot of different situations. You should be able to distinguish between an elastic and an inelastic collision, and you should be able to use this equation, which is demonstrating the law of conservation of momentum. So, if you have cars that are exploding apart, and we did this in the lab, you say, you got car B, you got car A. What direction will car B go when car A is propelled to the left? So if you release this spring right here and it pushes car A to the left, you won't all of a sudden see car B go to the left also when they're detached. Instead, what you'll see is you'll see car B go to the right. And you can kind of predict that. You can, in fact, we looked at what if car A is heavier? What if car B is heavier? What if you make one shoot fast? What happens to the other one? And what you tended to see was that momentum is conserved. In other words, the momentum of one car has to be equal to the momentum of the other car. And that's for closed isolated systems. Now, a closed isolated system is one in which it has no external forces. And by external forces, we mean things like friction, air resistance, outside forces like somebody coming and touching it. All those things are what are considered to be external forces. A closed isolated system particularly has no friction. That's a situation in which momentum is conserved. So if you're to look at this is how did the Explorer activity attempt to produce a closed isolated system? Now it depends on how you actually did it. If you did it the way we recommend, which is with the air track, you have air track or air that's blowing up right here that's reducing the friction that these wheels travel along. If you did it with something like a wooden track, you tended to see a greater friction value, so you didn't get as good of a data. But look at the lab that you did and try and figure out what attempts were made to turn it into a closed, isolated system. Whenever we're looking at momentum, a lot of times we're looking at collisions. Collisions are defined as either elastic or inelastic. An inelastic collision is when you have two things that collide and they stick together. So if you look right here, you have a car crashing into a tree. It's inelastic because they stick together. Now, in this case, they didn't move, the tree didn't move. But if you have something like if you shoot some Play-Doh at a box, what happens is the Play-Doh will hit the box and stick to it, and then they become one object. So an inelastic collision is it's defined as you have two objects before, and all of a sudden they combine into one object. An elastic collision is one in which objects collide and bounce off each other. Now, it's not that simple. You can't say that it's, oh, they bounce, so it's elastic. Because an elastic collision, and this is the key, is the one in which kinetic energy is conserved. So we'll do our conservation of momentum calculations, and if momentum is conserved or LOCM is upheld, and law of conservation of specifically kinetic energy is upheld, then that means that this is an elastic collision. Realistically, most collisions are somewhere in between. You're not going to have a collision in which two cars stick together and move together completely. You're not going to have collisions in which kinetic energy is always conserved. You're always going to lose something to heat, to sound, to some sort of deformation of the car. You're going to have some sort of thing. So most collisions end up being somewhere in between. So an example, this is the cue ball strikes the 8 ball, which is initially at rest, as indicated by the red arrow. The cue ball rebounds according to the blue arrow as shown. Predict the motion of the 8 ball. So you have the situation where you have momentum before. Momentum before is defined as, I'll change the color. Momentum is defined as this red arrow. Now, whenever we have this blue arrow, no matter what we do, we have to end up at this red arrow. So what I do is I say, okay, this is what I had as a result, is you had the cue ball bouncing backwards. If you had it bouncing backwards, what it means is that you had to have an additional momentum, and this will be the movement of the 8 ball that's like this. This is called vector addition. And what happens is the 8 ball will take this path right here as indicated by the orange arrow. Okay, and what that means is the momentum of the cue ball, which is the blue, plus the momentum of the orange ball, those together have to equal the momentum that you had before the collision occurred. And so that's why you can do this. It's called head to tail addition. Now, the reason why it's called head to tail addition, because people say, wait a second, you added the tails of the arrows together. No, no, what I was doing is I was showing that this is before the collision, right? This red arrow was before the collision. And then the two head to tail addition things are things that I did after the collision. So after the collision had to equal before the collision. So you can predict that the 8-ball would move this way. Now that does not include things like spinning or English on the ball, but it's just purely just hitting and bouncing off. This is a man and his son are stuck on a frozen pond. The boy, a physics prodigy, pushes his dad with a force of 50 newtons, so you have a force that's exerted this way. It says which will get off the pond if both, which one will get there first. So this is an example of momentum being conserved. So if you look before they start, the momentum is 0. Then the boy exerts a force on the dad of 50 newtons, and so as a result, he's going to have some sort of change in momentum. That change in momentum is then going to occur on the boy. And if you have equal changes in momentum, because together they have to add up to 0. So if you look, I have to have a positive change in momentum and I have to have a negative change in momentum. And they have to be the same value so that it cancels out to be the 0 that it was to begin with. Now, if you look at it, it says which one will get there first. Remember, the change in momentum can be equal to the mass times change in velocity. So whichever one has the smallest mass is going to have the greatest change in velocity. And this one says the roller skater shown below is initially traveling at constant velocity to the right. So she's traveling this way. She trips, and in order to regain her balance, she throws her trays forward. So the trays are thrown this way. So they're going to have some sort of change in momentum. Okay, there you're applying a force. There's going to be, the mass is going to move this direction. As a result, you want to know what will happen to her velocity. Well, she's going to have the exact same change in momentum in the opposite direction. So whenever you have a change in momentum of the opposite direction, what it's going to do is it's actually going to decrease her velocity, or it's going to make her slow down. It may actually make her go backwards depending on how fast she was going to begin with and how heavy the trays were. But she is going to see an immediate reduction in her velocity to the right. And the reason is you have this whole idea of conservation of momentum. The momentum that she's going to give the trays moving forward has to be canceled out by the momentum of her going backwards. In example A4, it says a ball of modeling clay is fired at a box at rest, as shown below. It says an inelastic collision occurs, which means you're going to have this clay actually come and it's going to stick to this box. It says describe the velocity including the direction of the clay blocks combination. So if you were to take a look here, this thing is initially at rest, so it has a velocity of 0. This is going to have some sort of positive velocity. What you're going to see is when this thing impacts it, this right here has a momentum of 0 to begin with. This one is going to have some sort of positive momentum. Now, whenever you take these things and you add them together, whenever they stick together, they still have to have that same positive momentum value because momentum is conserved. Okay, but it's going to have a much smaller velocity, and the reason why is you're going to have to add these two masses together. So it's going to have the same momentum as this clay block, but whenever you take that same momentum of the clay block and you divide it by the two masses that you have together, you're going to end up with a really, really small velocity. And this will be a little bit more evident whenever you look at some of the actual. So we come to our equation about the conservation of momentum, and it is m1v1i plus m2v2i plus m1v1f plus m2v2f. And it's somewhat complicated, but if you look at it in these terms, you basically have the mass of object 1 and the mass of object 1, which is this variable right here. You also have the mass of object 2 and the mass of object 2, which represents this variable right here. And then finally you have the initial velocity of object 1, the initial velocity of object 2, the final velocity of object 1, and the final velocity of object 2. So really there's no new variables, it's just kind of arranging them in this particular order. So one of the things that you need to realize about the conservation of momentum is it's not always quite this simple. So sometimes when you have what's called an inelastic collision, you have these two objects initially, And then what they do is they combine where it cancels out one of the things, and this becomes m1 plus m2. It can get somewhat complicated, but if you use this as kind of your base for what you're going to be doing, you can go from there. To kind of show you, it says two pool balls collide in a perfectly elastic collision as shown below. What is the velocity of each after the collision? Okay, this particular question says you have two pool balls that collide in a perfectly elastic collision as shown below. What is the velocity of each after the collision? So I'm actually trying to solve for the final velocity of object 1 and the final velocity of object 2 after the collision. So actually I'm trying to solve for two things, and this is going to be a pretty difficult question. So you need to keep a couple of things straight. So let's start off by identifying our given. And the first thing we have is we have the cue ball. The cue ball is object 1, and it's going to have a mass of 1.5 kilograms. That is not going to change. When you hit a cue ball, it doesn't all of a sudden break in half and have something less. And then you have object 2, which is going to have a mass of 1 kilogram. Okay, slightly different. Now, the initial velocity of object 1 is 10 meters per second. And the initial velocity of object 2 is going to be negative 20 meters per second. The reason for the negative is, remember, it's going in the opposite direction. Velocity is a vector, so your direction is important. So now what I want to do is I want to start off with what's my go-to at this point. I have the conservation of momentum. The conservation of momentum, or LOCM, Law of Conservation of Momentum, says that you have this. The mass of object 1 times the velocity of object 1, initial, plus the mass of object 2 times the initial velocity 2 initial equals the mass of object 1, velocity 1 final, plus the mass of object 2, velocity 2 final. And that can get kind of messy, but it's going to make a little bit more sense when we plug everything in. So when I plug it in, I can get 1.5 times 10 plus 1 times negative 20 equals 1.5 V1 plus 1 V2. Now if you notice, I left off the F's because in each case I know I'm trying to solve for the final velocity, and if I ever wonder, I can always just check up there with what I wrote. So that's the reason why I just left the F off, is just for brevity's sake, to make it a little bit easier to keep track of everything. So 1.5 times 10 is 15. 1 times negative 20 means you're going to be up with minus 20, equals 1.5 V1 plus V2. Now, I'm going to go ahead and simplify this a little bit, and when I do that, I'm going to end up with negative 5 equals 1.5 V2, or V2. Another way of expressing this is you can say, 1.5 V1 plus V2. As another way of expressing this would be that you can say that V2 is equal to negative 5 minus 1.5 V1. Okay. Now there's a problem with this particular equation. I've simplified it just about all I can, and if you notice, there's still two variables. So there's no way for me to be able to solve this because I just don't have enough information. So when I can't attack something with the law of conservation of momentum, my next choice is to go with the law of conservation of energy. In this particular case, since it is an elastic collision, it's an elastic collision, so we can say kinetic energy is conserved. Another way of saying that would be you have 1/2 m1 v1i squared plus 1/2 m2 v2i squared equals 1/2 m1 v1f squared plus 1/2 m2 v2f squared. Now, once again, this looks like it's a lot. It's not too bad. You're calculating the kinetic energy of each before and after the collision. So you just plug in your same numbers. 1/2 the mass times the velocity squared plus 1/2 the mass times the velocity squared equals 1/2 the mass times the velocity, the mass right here was 1.5 times the velocity squared plus 1/2 the mass times the velocity squared. Now if you look, I did the same trick right here where I left off the f's here, just for brevity's sake, once again, just to make sure I'm consistent throughout the problem. So now I want to go ahead and simplify it at this point, and when I simplify it, this ends up being 75, and you can check me in your calculator, plus this ends up being 200, and once again you can check me in your calculator. But then you have this right here. You have, I'm going to simplify this. What I'm going to do is I'm going to take these 1/2s and I'm going to pull them out to the front. So I'm going to factor them out. So you get 1/2, and then whatever's left is 1.5 v1 squared plus v2 squared. Okay, so I'm going to go ahead and simplify it a little bit more. I'm going to add these two things together, and then I'm going to multiply both sides by 2. And when I do this, this ends up being 550 equaling 1.5 v squared, v1 squared plus v2 squared. And at this point you're saying, wow, that's a lot of work and I haven't really accomplished anything. And you're right at this point. We still haven't accomplished anything. What I have is I have an equation with two variables that doesn't do anything for me, an equation with two variables that doesn't do anything for me. So at this point, this is where your math really comes into play. If you have two equations, you can set up what's called a system of equations, or you can solve by what's called substitution. So what I'm going to do is I'm going to take this thing right here, which I coincidentally solved for v2, and I'm going to plug it in for v2. So I'm going to have, change into a different color just so we know what we're doing, 550 equals 1.5 v1 squared plus, and now I'm going to plug in what v2 equals. -5 minus 1.5 v1 close parentheses squared. So what I did is I took what v2 equals from the momentum equation, plugged it into the kinetic energy equation, and now I have an equation that has only one variable. So the only variable that you have is this v1 term. So I'm trying to solve for the initial, or excuse me, the final velocity of the first object. So if you look at this, this can be kind of tricky now. So you need to know algebra at this point. It gets a little bit math intense if you didn't think so already. So you can say, okay, 550 equals 1.5 v1 squared plus, okay, now you're going to expand this polynomial, so you're going to FOIL it. So you'd end up getting 25 minus 3 v1 plus 2.25 v1 squared. Okay, so if you were to look at this, you can go ahead and combine these terms now. Okay, I'm going to combine my squared terms, which is here and here, and that right there gives me 3.75 v1 squared. And then you also have this term, which is by itself, and you have this term, which for now is by itself. Okay. When you go ahead and solve this, you realize that this is equal to 550, but this is a like term with this. So I'm going to do my best to go ahead and set those equal to each other. So now I'm going to have 0 equals 3.75 v1 squared minus 3vi, or excuse me, 3v1, this is a 1 by the way, 3v1 minus 525. So remember, I subtracted 550 from both sides. Now you may be saying to yourself, why did we do that? Remember, when you have a quadratic that's set equal to 0, you can use what's called the quadratic formula. You can attempt to go ahead and factor this, you're not going to get very far. So what we want to do is we want to set up our quadratic formula, which is x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a, where this term is the a, this term is the b, and this term is the c. So instead of solving for x, what I'm trying to solve for is v, but it makes no difference really. So now we plug in our number, so we say v1 equals, and then we have negative b. Well, my b is -3, so negative 3 is 3, plus or minus the square root of b squared, that would be 9, minus 4a, and then c, and my c is a negative 525, and that's real important. If you don't take the sign that goes with it, you're going to get an error in your calculator. And then divided by 2a. So this right here sets up the quadratic formula. When you solve this and you plug it into your calculator, there are going to be two possible answers. If you look, this is a plus or a minus. So one of the solutions is going to be negative 11.4389. The other solution is going to be a positive 12.15835. And so you have to decide which one of these is most likely to be it. So this is where it gets really tricky. So we've done the math at this point, and we know that these are two possible solutions according to the math. But let's go ahead and look back at the problem, and let's go ahead and see what we're solving for. So remember, we're trying to solve for V1, and that is a lot of math we have to scroll through. So we're trying to solve for V1. Now V1 is going to collide with this other ball. Is it likely that the ball is going to collide with this other ball and then continue moving at a faster velocity in the same direction? And the answer should be an obvious no, that that's not the case. That the ball should collide and then should bounce backwards with some sort of velocity. And so we know that backwards is in the negative direction for V1. So that means that V1 should have a negative velocity, which means that this is the only answer choice that would work. So I've solved for my V1 value, and that is a value of negative 11.4389. Okay, that's the velocity of V1. Now I need to solve for the velocity of V2, okay, which was the second part of this. Well, luckily, this is actually pretty easy. If you look, I already had an equation that I solved for V2, and that's this right here, okay? I had V2, remember V2 is equal to negative 5 minus 1.5 V1. So all I have to do is take this thing, multiply it by 1.5, and when I do that, you're going to get a pretty reasonable number. I would go ahead and, so you say negative 5 minus, and then 1.5 times V1. Remember, that's a negative number, so 1.5 times 11.4389 is going to be minus a negative 17.158. Okay. Well, if you look, you have a minus, minus a negative, so this is going to be plus a positive, and you're going to end up with a value of about 12.158. And when you do that, 12.158 represents the velocity of the 3 ball after the collision. If you think about it, when these things collide, this thing should hit and it should go backwards as well, so it should end with a positive velocity. Now this is a really, really tough question because it requires a lot from you. You have to use the law of conservation of momentum. You have to use the conservation of kinetic energy with an elastic collision. You have to use a system of equations, and you've got to use algebra to go ahead and solve for these particular answers. This is as tough as it gets. So if you're struggling right now, stay with me because the next couple of examples are much, much easier. In this one, it says a rock is initially at rest and explodes, sending 2 fragments to the left and 1 to the right as shown. What is the velocity of the fragment moving to the right? Well, what we want to do is we want to set up a conservation of energy again. So I'm going to start off with the idea that I have momentum to begin with, and I have momentum that I end with. Okay, to begin with, I have momentum of 0. And that's because this thing right here is at rest. It's stationary. So no matter what, the momentum that I have is 0. So that means that when I add all the pieces and fragments together, then the resulting momentum has to be 0 as well. So now I want to look at all the pieces. And I'm going to define left as being negative, and I want to define right as positive. That only matters in terms of the velocity. So now let's go ahead and take a look at what we've got. So the mass of the first object, so I'm going to find the momentum of each piece, this piece, and then this piece, and kind of combine them all, because this is after the explosion. So I would say the mass of the first piece times the velocity of the first piece. Notice how it's negative because I defined left as negative, plus 0.75 times negative 100 plus, now I don't have the mass, it's not listed, but remember I had 5 kilograms of mass, and those 5 kilograms of mass have to be somewhere. So when I take a look at this, I'm going to go ahead and say that this is 3 kilograms, because that's what's left, times some unknown velocity. So if you look, you can go ahead and calculate this out. You would say 1.25 times 40, and if you were to do that, you would get something like 50, but remember it's negative, and then plus 0.75 times 100, but remember it's negative, so it'd be negative 75, plus 3v together has to equal 0. So you're looking at something that's much, much, much simpler than the last example. So now you can combine these terms. I'm going to move both of them to the other side. So I'm going to add 50 and I'm going to add 75 to both sides. And when I do that, I get 125 equals 3v. You would divide both sides by 3. And when you do that, you get something like 42, something around 42. You're going to have a little bit of a fraction there, or a little bit of a repeating decimal that you don't want to deal with. But, excuse me, well, it's about 42. It's really 41.67, but that's roughly 42. So this right here represents the velocity of the larger fragment. And it makes sense that if you have a larger fragment, it's going to be moving slower than most of the smaller fragments. And people say, but what about this one? Remember, these two are going in the same direction, so they can be thought of as one fragment for the most part, except for the fact of the velocities. Be very, very careful when you're doing momentum questions in terms of directions of velocity, in terms of negatives and positives. It becomes really, really important. In our last example, we have a 0.05 kilogram bullet that is fired at a 5 kilogram wooden block with a velocity of 100 meters per second. The wooden block is initially at rest, so this thing right here is at rest, and it says what is the velocity, including direction, of the bullet block combination. So, once again, we're going to kind of set this up as conservation of momentum. Okay, now I have two objects beforehand. I've got the bullet, which has a mass of 0.05. I have the velocity of that particular bullet as being 100 meters per second. And then I can add, once I add, I can say the momentum of the block. Because remember, this is the bullet. Now the momentum of the block is 0. The momentum of the block is 0 because it says it's initially at rest. Remember, an object has to be moving for it to have momentum. Now, the bullet embeds itself in the block. Okay, so because it says bullet block combination. So after the collision occurs, they are going to stick together. So this is an inelastic collision. So I actually need to add their masses together. So I'm going to end up with a mass of 5.05. That's the mass of the wooden block plus the mass of the bullet. Now together those things are going to have a velocity that I'm going to call v. So when you multiply this out, you're going to have 5 plus 0 equals 5.05 v. You're going to divide both sides by 5.05. And when you divide both sides by 5.05, you're going to end up with something really close to 1. And it ends up being a velocity of about 0.99 meters per second. Okay, this right here is the level of question that you're going to be expected to do on your test, along with this level of question right here. Okay, this right here is considered to be a bonus level question, but you should be able to do this by the time you get to the test as well. This one is going to require a lot more work and a lot more practice. You need to be able to do all the pieces in order to get to where you want to go. But this is as tough as it gets. So